Okay, so I'm going to start the talk before Fedor comes in talking about directional dynamic games, how to solve them, how to estimate them. But we're going to start pretty simple. Okay, so so first I'm going to talk about the challenges of the estimation of dynamic discrete game. Oh, sorry, static discrete games. When you have multiplicity of equilibria, it turns out that there's some challenges in terms of both solving the model you would have to imagine that will arise in a dynamic model. Here we can do it very easily, but also some econometric issues. Okay, so we're going to compare a variety of different estimators, and that's actually already done in this very nice paper by Schjerning. Okay. So Schjerning Su is kind of the founding father of this, together with Ken Judd, with the mathematical programming with equilibrium constraints. Unfortunately, we don't have him with us anymore, and died way too young, but his paper is still there, and I'm gonna go through that. Okay, so it's also in the box. Anyway, so we have a variety of different ways to estimate both static and dynamic games. We're gonna characterize them into two-step CCP type of estimators. And then this work by Girigiri and Mira, it's kind of updating recursively the conditional choice probabilities in order to improve the efficiency of the estimate. So we're going to compare the two-step estimators to a full-blown maximum likelihood, and that's what Schjerning Su is doing in this 2013 paper, and there's also one for dynamic models with the baseline C. And then we'll compare it with the nested fixed point algorithm that requires us to solve for all the equilibrium models. Okay, so we're gonna go really, really simple now. Okay, it's very, very simple static game. I think it's sufficient to illustrate some of the issues that arise when you want to estimate models with multiplicity of equilibria. So we have two firms, A and B, and both of them just take binary reactions whether or not to be active in the market. So you have DA, that's one if firm A is active in the market, and DB, that's equal to one if firm B is active in the market. Now they have some payoff functions, and it's a game, so the payoff of firm A depends on the decision of whether firm B is actually active in the market. Okay, and then these coefficients, alpha and beta, kind of determines what the monopoly and duopoly profits is going to be. And so what we're interested in estimating is these parameters, alpha and beta. Okay, and then there's some we can alpha some heterogeneity. This, think of these as types of different firms, and here the two firms, they both observe these axes. Okay, think about the size of the firm or the type of the firm. And then we got our ID extreme value shocks. Okay, so we got choice. So we got the choice probability is going to be low, okay? Just like the likelihood. Okay, so these are going to be private information, and they're observed only by each firm. So it's kind of a game of the incomplete information, and the acquisition doesn't observe it either. Just the choice probabilities of potential identifiable. And this is just scalars. It's a very, very simple problem. Okay, so if they have this ID extreme value distribution, well, we're going to get Bayes-Nash equilibrium conditions that satisfy this. Okay, so the choice probabilities or the best response functions is going to be locus formulas, the functions of the other investment probability for the other. Okay. So here, and we're going to call that psi A for firm A, the best response function of firm A, and then the best response function of firm B, that's psi B. And then wherever you have mutual best responses, these two best response functions are crossing each other. Okay, so here's some parameter. Alpha is equal to 5 in the game we're going to look at throughout, and then we have beta equal to -11. So this is, you're really going to be hit by a hammer if the other guy is there. So it's a very contestable anti-coordination game. And then we have two different types of firms. One is just have a little bit of bigger X than the other. Okay, so if we look at the best response functions, you see here this multiplicity of equilibria. These best response functions, they are crossing each other in 3 different points, and then you see here this equilibrium where firm 1 or firm A is investing with a very low probability, and the other firm in that is investing in with a high probability or in being active in the market, and vice versa in this other equilibrium. And these are stable equilibria, and then there's an unstable equilibrium in the middle. So there's 3 equilibria, and they're pretty easy to find in this example. Okay, so I mean, one way to find it would be just substitute one best response function into each other, find the fixed point where that mapping kind of maps into itself. So 3 equilibria. Okay, that's well, you can devise an algorithm to find that. That's pretty easy. You can start here and 1 and do the successive approximation. Starting from here, you can find that equilibrium. If you start from the other end, you're going to find that the other equilibrium, and then you can find some bracketing or bisection algorithms to find the one in the middle. Okay, so we have a surefire way to find all these equilibria. It's not that hard. Okay, so let's do some Monte Carlo. Okay, so we're going to look at a data generating process where the data is generated first by a single equilibrium. So one of these 3 equilibria that you see, we can generate data from these. That would be, just generating zeros and ones based on these choice probabilities or investment probabilities of firm 1 or firm A and firm B corresponding to each of these 3 different equilibria. So we're going to do that one by one. And we're going to assume that these 2 players, they use the same equilibria and they just play it 1,000 times. So we have a data set that consists of the actions of the players, these discrete choices 1,000 times together with X that we're just going to keep fixed. So given these data, can we then hope to estimate the structure parameters? Seems like a pretty easy deal. Okay, and it is in this case. So let's write out the likelihood. Okay, so if you want to do maximum likelihood, well, you got a discrete choice likelihood for 2 players with these investment probabilities entering into this log likelihood function right there. Okay, and they are solutions to these 2 sets of equations. So the parameters we're looking for, alpha and beta, well, they obviously affect this best response function, so also the solutions. Okay, so the investment probabilities here, well, they are affected by these structure parameters. So they are like implicit functions, just like we have the expected value function or integrated value function in the Harris-Sachar model with function of the implicit function of the parameters. These are going to be implicit function of these parameters as well. Okay. So we just want to maximize this with respect to alpha and beta, and then see how does that look like. Okay, you can do that with the nested fixed point algorithm. So that involves calculating that likelihood, but for each value of those likelihoods, for each value of the parameters, you need to calculate all these equilibria. That is the potential 3 solutions there'll be for each parameter's trial value. And then we select the equilibrium that is most likely to be observed in the data. That is the equilibrium selection rule that maximizes the likelihood. Okay. And then our PA and PB, well, these are the investment probabilities associated with that selected equilibrium, and then we maximize that function. Looks like this. And this is the data when it's or the likelihood function when data is generated from equilibrium number 1. Nice and smooth. Okay. You got alpha, you got beta, and it looks like that if you find the top of that function, it is pretty close to the true value. You can use a standard gradient-based solver to find that maximum. Well, look at this. That's a likelihood function when the data is generated from equilibrium number 2. There's a cliff. And the true value is actually right at the edge of it. This poses several problems. First of all, how do you even, we can rule out using a gradient-based solver to maximize this function. Okay. But let's before we just think about how to find that maximum, just think about how does that arise? Why is there a drop in the likelihood function? In this case, where we have generated the data from equilibrium number 2. Let's look at the best response function, or the second order best response function, whatever fi first, this one. So the data is generated from an investment probability firm 1 that's around 0.6, and the corresponding investment probability firm 2. But these lines are going to move as you move around the parameters. So let's try to change beta a little bit. And see here if it works. I don't know, is this visible? This is what we had in the first place, right? The bigger figure, but I hope you can see it. Okay, so why don't we try to change beta here? Just lower it a little bit so the game becomes less contestable. Corresponding action to move in the direction of the cliff. See, okay, what happens is when I run this again, choose my best response function. And whoopsie, 2 of these equilibria just disappeared because you changed the parameters. That's why you can find in the, that high investment probability for firm A, as a solution for the model, because you change the parameters. Now you have suddenly a discrete jump, a discontinuity in the likelihood function. Okay, so that's a challenge. And it's not actually different from equilibrium. You may think this is just because of the instability of the equilibrium, but it's not. It's just because you change parameters and then these 2 equilibria disappear at the same time. So it's going to happen also for equilibrium 3. Okay. Now that's one way to estimate it. And you can see why it's potentially challenging to search over find the maximum of this discontinuous function. Okay, so another way to do it would be via impact. So what do you do when you do impact? You search over the parameters, but you also search over the solutions of the models, these PA and PB, right? And the likelihood function here, well, that's where you have PA and PB. This is completely smooth in the in these 2 investment probabilities. And you look at the constraints, well, everything is nice and smooth here as well. So you can use a gradient-based solver, constraint optimized solver. So you need to impose these 2 constraints while you're doing that. Let's see how that goes. You can generate beta, estimate the model for the parameters right back. And so here we have alpha, true value is 5. And it seems to kind of nail it in all these different cases. You have these 2 different implementations supposed to give the same thing. Okay. So and these are generated from each of these different equilibria. It was easy to do the nested fixed point algorithm here, right? Because we could easily calculate all these macro-perfect equilibria, and it's not that hard to use Meldoni to something to maximize this particular function. Of course, these plotting is going to be amplified by orders of magnitudes when you go to dynamic games, because then it's not 2 scalars, it's two functions for each of the 2 firms that depends on all the states. That depends on all the states. Okay, and there'll be multiple functions if there are multiple equilibria. Okay, so some remarks. The likelihood is discontinuous for when you take the upper envelope of these equilibrium-specific likelihoods. That's just because of that max over integer. We haven't shown the impact likelihood, but it is smooth. but you can have problems with local minimum. Okay, so I'll show you that it doesn't always work, even though it does work pretty good if you have very good starting values. Okay. Now we have to think about how to do inference. One of the we're supposed to have these two assumptions satisfied, right? That the parameters are identifiable, the model is well specified, and we have random sampling, and then there's a bunch of regularity conditions. And when I look at the textbook, one of these conditions is that the objective function is differentiable in the interior of the parameter space. And then, of course, when we talk about asymptotic normality, as n goes to infinity, it is kind of differentiable, right? If it's not right at the clip. But there's some stuff to think about. And secondly, this problem is just extremely simple, and these problems here, they're going to be amplified by orders of magnitude. Okay, so let's go to multiple markets. Okay, so now these firms, we have various different markets. That could be, in this case, there's 25 of them, and they vary by what the types of the firms are. Okay, so we just generate a grid with 5 grid points on an interval, and then we take out all these combinations of firm type 1 and firm type 2 to generate 25 combinations, and that's the way we generate these data. Okay, and this is all fixed and observed. Okay, we use the same structural parameters as before, and then for each of these markets, we solve the model and generate all the equilibria. There could potentially be 3 of them. And then we just randomly select an equilibrium from each of these markets to be played out in the data when we generate the data. Okay, and we do that 1,000 times and then we try to see if we can estimate the model. When we select the equilibria in the data, we just flip a column. And there's multiple equilibria for various combinations of XA and XB. Sometimes there's 0, sometimes there's 3. And of course, if XA and XB is very low, it's like you have only the epsilon shock left, so there's no strategic room for investment. That's just like firms are flipping coins in order to figure out whether they want to be in the market. So that's a unique equilibrium. But then you start to move in the range where bigger values of XA and XB, then you get multiplicity of equilibria. Okay, now estimation with multiple markets for n of xp. Well, it's similar to the likelihood function. It depends on now these market-specific investment probabilities, again, functions of the structural parameters. And then for each of these markets, we select the equilibrium that is most likely to be played in the data. So again, this requires us to solve for all these equilibria at each of these m markets. Okay, so that's kind of the brute force way to do this. So we can do it. Okay, we could also do MPAC. And again, the constraint optimization problem. Well, that involves searching over the parameters, the alpha and beta, and also these investment probabilities. But now these investment probabilities are vectors. There's a potential 1 for each of these different these different markets. So that's now 2 plus 2m parameters. Okay, investment probability for each firms subject to the constraint of the Spatial-Nash equation needs to hold. Okay, so MPAC does not explicitly solve these as you would do with the nested fixed point algorithm for each trial parameter. You just have to hold at the end. So that's a promise of MPAC that we're able to save a little bit of the computation in order to not have to solve these equations for every combination of parameter values that are optimized and searchable. And it's supposed to be, it is the same implementation of the same maximum likelihood estimate. It's just 2 different ways of obtaining it. So here's what we get. for the nested fixed point algorithm. True alpha is 5. And sorry for the mess here. This is homemade. So it's kind of in the ballpark. Okay, so it's around the same. It doesn't really kicks off and find completely different parameters. And if you look at the investment probabilities, they're very close to those equilibria that generated the data. Okay, so this is both for alpha and beta. Here's what you get with MPEG. Well, alpha does not look too bad, although the range is bigger. It's supposed to implement the same estimate. So something is going on here. You look at beta, there is a much more variety, and sometimes these equilibria involves, or sometimes the parameter estimates are quite far from the true value. Now, it's not like I just generated data, estimated model with MPEG, and didn't let it converge. These the equilibrium conditions, they are satisfied of all these estimates. Okay. So it's just because it's selecting the wrong equilibrium. Okay, maximizing, finding a local maximum to the likelihood function. Okay, local maximum where the where these equilibrium conditions are satisfied.
How do we know it's not lack of identification? And how do we know it's?
Well, it's the same model, right? I just estimated with NFXP. So that algorithm was able to get the parameters right. And there's a lot of data. It's not hard to estimate these investment probabilities and back out those parameters. If you were to estimate the model with CCP, it would nail it right away. You would be able to identify in the data what was the actual equilibrium plate. Yeah, we basically observe it and with these investment probabilities. So I don't think it's because of identification. This is because MPEG sometimes find a local minimum. And it's hard to detect without just trying other starting values. Because it does look right. I mean, it looks like it maximized the function and the equilibrium conditions were actually satisfied. Here you can see for MPEG what is going wrong. So here you got the true investment probability from A minus the estimated one, and there's a wide distribution. Sometimes it just select the other equilibrium and find the local maximum of that likelihood function for the wrong selected equilibrium. I'm not saying MPEG is a fantastic tool, right? Especially if you have very, very good starting values for these investment probabilities, for example. It's just you have to be careful when you use it that it is actually consistent. Okay, so here's a little bit of a conclusion on comparison of these two methods. So you've got NFXP, well, it has to search over two variables, the two structural parameters. MPEG, well, it's a constraint optimization problem. There are more variables. There's the two structural parameters, and then there's m investment probabilities for each of the players. So that's 2 plus n. Okay, so for multiple market, that kind of grows. It can be done here in this medium size exam. Okay, now we can't estimate the equilibrium plate in the data. Okay, let's highlight another thing here. Okay, in order to do NFXP, you need to find all the equilibrium. That's really a downside, right? If there's only 3 equilibrium. But if you have a dynamic game where all this stuff is multiplying, there could be sometimes fantasilions of equilibrium. Computing all of them can be a really, really hard computational task. And you need to do it for all these different combinations of the structural parameters. Okay, and we have problems with local minima. Okay, so I did this in MATLAB. I'm sure there'll be software that's better than fmin under nitro that I'll be using. Okay. Or you can use a global search. It's not so much the point, it's just be aware you find the global maximum likelihood. Okay, so we have two-step estimators, this least square type estimators. You go out, you estimate the CCPs, and then you solve this this least square problem. Or you can do pseudo maximum likelihood. Okay, again, you go out, estimate the CCPs. Okay, well, they're not that conditional here. It's just scalars. So the investment probabilities. And then instead of using the solution for the Bayesian-Nash equilibrium as implicit function as a of the parameters inside the likelihood function, you make a pseudo likelihood where you just fix those conditional choice probabilities in the Bayesian-Nash equilibrium equations, and then you search over the structural parameters using those choice probabilities. That kind of makes it much simpler. Okay. If we were to do a Monte Carlo, I'm not showing you here, this works in this little example. There's some issues with finite sample bias. It uses more of the information if you're doing full maximum likelihood estimator, if you're willing to make assumptions, parametric assumptions. One way to kind of improve on that is to do the nested pseudo likelihood suggested by Iskhakov and Mueller. First done in single agent models in 2002, and then this is two-step estimator for, or sequence of two-step estimator for games, and that Econometrica paper 2007. So, of course, this is for dynamic games. We're going to use it in our little simple example. The idea is now, the Bayesian, if you were to go and estimate this model, estimate the CCPs, you got your non-parametric estimates first, but then the model, when you have estimated the structural parameters using your two-step estimator, well, it may be that the model predicts another set of equilibrium conditions because these equilibrium conditions are not necessarily satisfied at our non-parametric estimates of the condition choice probabilities. So why don't we just use this and see how it goes? We try to put that, initialize a two-step CCP type estimator and make it a three-step CCP estimator. And then there's sequence, and then supposed to converge to maximum likelihood. Now that goes fine with equilibrium number 2, equilibrium number 1. But once you start to iterate and you work with this unstable equilibrium, you get results all over the place. That's what they also report in this paper by Chiu and Su, and the paper, the version with the dynamic games by News Deadlines. Okay, so it's finding incredibly unstable. This method like Kasahara and Schmatzer has a way of dampening this. It doesn't help. Okay, it helped a little bit, but it doesn't solve the problem. And this is not because it's a stable equilibrium, unstable equilibrium. It also happened when we generate data from equilibrium number 3, because if you have a little bit poor starting in this, if you recall the best response function, you just start a little bit to the left, you kind of converge to the wrong equilibrium, you can get stuck there, and that's what happens. Okay, so I think I better give the floor to Fedor now. And I'll set all I want. Okay. Oh, question?
Yeah, so I know that my understanding is that this problem with the Equilibrium mirror and maybe it's also true for M-types, especially when there's high interaction, large interactions. Right? If you start out with no interaction, no problem, right? You need equilibrium. And
yeah, that's
you only get unique equilibrium, not unique equilibrium, and there's imperfect information here when you have a lot of interactions between and like in the Equilibrium mirror paper, you know, and their empirical results, there was no evidence of that kind of high interactions.
No, fair enough. I'm trying to illustrate a point here that happens when you have a very contestable game, and this is, I mean, we're really hitting the duopolist with a hammer, right? They lose 11 instead of getting 5. So of course these parameters are chosen so we can generate a case where you have lots of multiplicity.
can you fix MFEX by doing, I mean, the nested fixed point algorithm kind of requires, it's kind of built into it to be careful about looking, you know, and running it all the way, starting at different starting values. Can you fix MFEX by just fixing?
Okay, so let's suppose that we observed the true investment probabilities. We just have so much data. We could initialize it with a CCP type estimator. We get within a domain of attraction, and that's actually what we do. So the more data that you get, the more likely it is that you would be able to get impact to conversion. That's also why you see it here happening in the case with the multiple market. First of all, it's a high dimensional problem. And second of all, you have to estimate more parameters to get like good starting values.
No more questions, then we'll continue. So I'm going to use just about a little bit over 100 slides in the next hour to talk to you about the dynamic version of a similar problems. And we're going to use this Bertrand pricing and investment game, which we also labeled leapfrogging game, as a leading example. And you know, in the framework that Ariel has put in front of us last lecture, we are doing this, you know, going back to the brute force approach, and we're going back to the mark of perfect equilibrium. So you can think of this exercise here as probably a test of what you can really do with the full solution methods. And the takeaway point here is that, well, first of all, it is extremely computationally intensive and hard. Whether there is a practical application, we are kind of still investigating that. But the takeaway is that sometimes the structure of the problem allows you to go a lot further in the full solution approach than you can in the general setting. And so I'm going to be talking a lot about the structure of the problem, and that's where the directional dynamic games come from, right? So we're talking about very specific class of games here. And then this approach also allows us to be extremely serious about multiplicity of equilibria. So we're gonna attack the problem of the multiplicity, you know, the best way possible. And then this then creates the playbed where we can check different estimation techniques, different estimators, and see how they perform their relative performance in this really hard conditions, similar to what Bertel had shown for the static games. Okay, but let me take one slide and go back to relate the concept of multiplicity to the market design theme of the conference. You know, Satterwhite and Williams in 2002, in the version which is not the published version, they have a numerical example where they, you know, the paper talks about the optimality of the K double auction mechanism. And here are two examples that they compute for different what they call environments, which are the distribution of valuations for buyers and sellers. And you can see here multiple lines in the solution for different number of players in the market. You have to look at all equilibria if you're talking about convergence to the truth telling, which is a diagonal in each of these panels. So kind of keeping in mind the worst case, not only in terms of the environment of the problem, but also in terms of the outcome, the equilibrium outcome seems to be important there as well. All right, so like I said, this is a very a specific example, and overall we are doing kind of computational theory, right? We are coming up with methods how to deal in full solution framework, how to deal with a problem and try to be efficient. And in that sense, it's quite theoretical. Now, it is extremely practical. It's just quite opposite. So it comes from this very specific collusion case among the Australian cardboard producers. Australian market only has really two firms which produce cardboard and make boxes out of them. And they have colluded between 2000 and 2005. They divided the market. You know, I'm going to just give a very brief description of what happened here. And if you're interested in juicy details, talk to John in the break. He can provide a lot of interesting details. I have a question. You know?
We could rule this up, but you would have thought that estimation would have been because there's multiplicity and it's not all this time, which not where you are. You would use something like first order conditions to get estimation. You get the equilibrium, and you to actually get the parameters. All I need is something like first order conditions. And that'll be true regardless of the equilibrium. So I didn't quite understand.
So so what are we doing? What can we offer in addition to the first order conditions estimation? We can allow multiple markets playing different equilibria. So by solving the models.
Yeah, the first order conditions has to be satisfied no matter where you put it. I mean,
Okay, so that
focus on getting the equilibrium, that's different. But I mean, if you're
Right.
just the estimation, I don't understand.
right. Can I say then? Okay, I thank you for this point. Yeah. We will be able to do counterfactuals, of course, by looking at all of the equilibrium. But yeah.
Go ahead. It's okay, we can talk about it.
All right. This market is quite specific in the sense that neither Amcor nor Visi are doing research and development. So what do they do instead? They are buying machines from Germany, essentially, which allows them to reduce the marginal cost of production. And this is a homogeneous good. You know, the constant terms to scale seems to be a reasonable assumption. So this is what I said already, right? But so the dynamics in this model come from the fact that, you know, there's this state-of-the-art process which the firms don't control, and they can tap into this state-of-the-art production technology that is developed elsewhere by essentially doing very simple binary choices. Do I buy the state-of-the-art technology and become a cost leader, right? Or I just stay where we are and we keep the structure of the problem as it is. Now, this kind of makes you think of the leapfrogging equilibrium in the sense that as time goes by, right, there is a cost leader and a cost follower in this duopoly, and some stochastic process behind the scene improves the possibilities of the marginal cost of production. And then, you know, at some point the cost follower could have invested or can invest and leapfrog, become the cost leader in this industry and start earning some profit for, you know, some period of time. Now there's a paradox, right? Why would you invest in the first case if you know that your competitor can do the same, can also do the investment maybe next year or maybe this year in principle, and then you're on the same level of the marginal costs and nobody's earning any profits? And, you know, we are assuming Bertrand competition among the consumers, and since this product is so simple and homogeneous, then it's reasonable to assume that consumers are just buying from the lower price. All right, so that's kind of the theoretical question. How does this industry operate, and what kind of equilibria can be sustained in this environment? All right. Do I have any questions about the structure? If not, let's formalize the problem and start putting down symbols and do some math. So we have we don't have entry or exit. So this, you can think of this as a quite simplified version of what Ariel was talking about just last lecture. So first of all, we don't have entry exit. We have discrete time, infinite horizons, only two firms, and that's fixed. Right, and the choices that these firms make, these are the price of the product that they offer on the market, and whether or not to buy this exogenously evolving state-of-the-art technology. And so the choices are also very simple. They just, you know, binary, yes or no. We assume static Bertrand price competition in each period. So there is no brand loyalty or switching cost or anything like that. So the whole market switches to the lower price producer of cardboard. Let's talk about the state of the art production cost. we have to think about some initial states. So this is marked C naught, and without loss of generality, really, there's some lower bound. Let it be 0. So this is the interval where the progress in this cardboard production technology is happening, is defined. We will discretize it, so we will make it a discrete problem, discrete game, and there will be some transition probabilities. Pi defined here. Well, what's important? Oh, sorry. What's important to say about pi is that there is no way back. If the improvement has happened, there is a 0 probability that the state of the art can go back to the higher levels of C. Okay, that's clear? That's the key assumption here. All right, and then we assume there is some investment cost KFC. What is 1 period construction time? So if you decide to buy new plant today, then in the next period it will become operational. And so the structure of the industry is given by this vector of 3 numbers, right? C1, C2. This describe the costs for the 2 producers, and we have the state of the art. Now the whole state space is what we call the quarter pyramid, right? This is a 3-dimensional object with the obvious constraints imposed. Nobody can be better than the state of the art. And in the spirit of everything that we've mentioned by now, we have private information in the form of the extreme value type 1 shocks, which will lead to the convenient logit investment choice probabilities. Eta here is the scaling factor, and we will consider both the deterministic problem and the stochastic investments problem. All right, now it turns out that if we assume Bertrand on the primary market, then we can just write the expression for the profits in each time period. And then we don't really have to think about the choice of the price, right? The cost leader gets the whole market and earns the difference between the costs. The market is normalized to unity. What's more interesting is how do we think about the investments? And so here we can think of simultaneous investments, simultaneous moves. But just to get a bigger picture, let's also think about the alternating move setting. And this is essentially that, in one time period, only one firm can make an investment. And then we need this additional state variable we call M, right? Which kind of marks which firm has the right of move in this period. And, let it be an exogenous Markov process, which includes, of course, alternating moves or the situation when only one firm is even allowed to make an investment. So this is quite general. All right, so here we have the two choices. And as I said, we're going to kind of not think about the price choice at all, but the strategy profile is a pair of the strategies where each strategy is defined as is the choice of the investment action probability and the price. And coming back to the standard, we're using the standard definition of the Markov perfect equilibrium. Right, the equilibrium is a pair of the strategy profiles and the value functions such that each agent is maximizing their intemporal behavior and also doing that as part of mutual best responses. All right. Right, so let's write the Bellman equations. So imagine that, as I already said, that the structure of the industry is given by the 3 numbers, C1, C2, and C. And let me not think about the M, the order of move, just for easier presentation. You can go back to the paper and get a lot more details. I'm actually skipping over a bunch of additional details here. But essentially, we have a maximization over 2 different actions. Oh, I should point using the computer for the online audience. So this small v denotes the deterministic part of the value, right? It depends on the state of the industry, and you have the investment side. You're choosing between the investment today and not investing today. In both cases, you get the instantaneous profit because of the time to build. So in the current period, everybody gets the R corresponding I of C1, C2. If the investment choice is made, then there is a cost of this investment, K of C, and there is a discounted expected value from the future of this choice. And you can see that this EV function is conditional on the current choice NOI. Okay, and already this gives us the standard logit choice probabilities that we have. And remember about the eta, the scale of the extreme value type shock. Right, but and let's look at what are these expected values. Well, conditional on investment, I'm sorry, on not investment, what can happen in the future is that we have to see how the C1, C2, C today kind of translates into the future values. And then we have to integrate over the actions of the other player and over the transition of the state space, which is independent of those actions. So that's what we're doing. So imagine that the firm I, which is 1, for easier notation here, is not investing, and that means that C1 transfers into C1 in the future, okay, into this blue state variable. And conversely, if there's an investment, then the next period starts with the state-of-the-art production cost for firm 1. And then we have two actions of firm 2, right? With the probability PJI, there's an investment which makes C2 equal to the state-of-the-art C. And then the probability of not investing, that C2 remains in place. And same thing over here. And now finally, the integral is just the integral over the possible transitions of the state-of-the-art. Okay, that's all it is, really. 3 things that can happen. In the alternating move game, there is also additional Markov chain which is imposed on the order of moves. So that makes things a little bit more complicated. Well, going again, what is this H function? Well, that's just the expectation of the maximum value of the choice tomorrow. And with the extreme value assumptions, this is just given by the log sum.
But I must be confused. The 2 right-hand sides are the same. So it should be something different.
Yeah, this is conditioned on not investing and no, the right-hand side, right? Observe here, this is the difference.
Oh, I see. Okay.
So this case, for example, this case here describes the future when both firms invested, right? And they get to the same level of the marginal cost of production. This case is when neither of them invested. All right, so that's about all the math that I wanted to show you, and I'll start showing pictures next. So let's try to visualize this problem to get a better feel of what's going on. As I said, the state space is given by 3 numbers, so we're going to start drawing this pyramid. And the axes are rotated in a slightly awkward way, but on the vertical one is the state of the art. Okay, and 2 horizontal ones, these are the current marginal cost of production of the 2 competitors. And let's just look at the possible dynamics of this game, right? So we assume that everything starts, we set everything to start from the apex, where the state of the art is C0, and the firms also have the same marginal cost of production. And this dot, that's the dot which signifies the state of 333, right, in this example. The problem can remain there for as many periods as it happens. Time is completely separate from these transitions, right? But at some point, there is a technological improvement, and state of the art becomes lower. And so the whole industry transfers into this new point. Oh, I should be pointing on the computer. New point, which is marked yellow here. And this is the color we use for the interior points, where both firms' marginal cost of production are below the current state of the art. Okay. And again, maybe these competitors had waited for some time, and there's suddenly an improvement, or finally an improvement, and they've just decided to invest both of them in the same time. And that's a transition along the horizontal plane, cutting this pyramid to the corner point, where both of the firms made the investment, and again, both of them have the same cost as the marginal cost. I'm sorry, the state-of-the-art marginal cost. And maybe the problem sat there for some time, right? So several periods. And at some point, there's a new technological improvement. Okay, and with the new technological improvement, we again fall through to the next level of this discretized state space, where the state of the art is again in front, below of the costs of the existing costs of production. Well, imagine then firm one makes the investment and transfers to this edge, the point of the state space, where one of the firms is a cost leader, in this case, firm one. You can see that firm one has the cost one. And again, time passes by, and at some point there's another technological improvement. And imagine that now firm two makes the investment, taking the whole problem, the whole system into another edge point. And this is the case, this is the instance of leapfrogging, right? We have a new cost leader in this industry. And at some point, maybe there's another investment. This would be for idiosyncratic reasons, because nothing really changed in the payoffs. Here, firm two, firm one, which made the investment, their profits did not change, because now we are again at the edge point of the state space, where nobody's making profits because everybody's costs are equal. All right, so this gives you a sense of how this dynamic game transfers to the state space. Imagine now we have a lot more points, a lot more possible paths, but the key property here is that we are sort of going in one direction, and at some point may reach a set of states, a set of points in the state space, which is absorbing. So there are no more transitions possible once we reach this edge, because technological progress cannot go below zero, below the lower bound. All right? And this is the notion of directionality of this dynamic game that we want to work with. All right, so I'd like to make it a little bit more general. And so let's look at the different levels of this pyramid. They correspond to different levels of the state-of-the-art cost. Okay, and I want to make a flat graph and talk about directional games in kind of more generally. Now, this rectangles, they correspond to the different layers of the pyramid. All right. And the errors are the transitions. I've drawn these errors. They correspond to the transitions through the pyramid, which correspond to the technological improvement. And so, as we saw before in the example, technological improvement takes the problem from the edges and the corners back into the interior of the layer, into this yellow dots. All right. Now imagine that firm one adopts a strategy when they make an investment, they buy the new technology in every interior point. Okay, that's their strategy with some probabilities. That means that with some probabilities, the structure of the industry will shift along this new added errors. And imagine that firm two, adopts another strategy to invest in all of the edge points which are reachable. Okay, so what we are left with? We're left with a partial order on the points in the state space, which is corresponding to a given strategy profile. All right. And we have to think about this partial orders induced by different strategies to really define a directional dynamic game in general. So there are two conditions that we impose on this partial orders, strategy-specific partial orders, in order to have a finite state stochastic game being directional. Well, we do allow for self-loops, right? These little self-loops, they correspond to the problem staying in the same point for several time periods. But we cannot allow the loops which create, a loop through several points in the state space shown over here. And so this anti-cycling condition is one of the conditions in the definition of the directional games. Another one is that we need pairwise consistency. We cannot have two different profiles, strategy profiles, which induce opposite transitions between the state points. Okay. And so now we can say, what is a directional dynamic game? Well, it's a finite state Markovian stochastic game where these two conditions satisfy for every admissible Markovian strategy or a pair of them. Right? Now it's is it possible to take a game and kind of check whether these conditions are satisfied? And it requires you to look at all possible strategies. And you can think of algorithms to do that, working on directed graphs. trying to find loops in them. Or maybe you can, like in this example, just kind of go through all possibilities and exclude the possibility of a loop with an argument. Now, on this, is it the only game that we have, the leapfrogging game, that is directional? Well, no. So, for example, a couple of examples here. Dube, Hitch and Günther in 2010. This is a tipping point game where the adoption of a gaming platform, the value of adoption depends on the market share of earlier adopters through availability of games for that particular platform. And if you draw the state space of this game over here, then you see that the points on the diagonal, these are the points that sort of constitutes the stages through which the industry develops. And there's no way, well, you have to assume that people don't switch between the platforms and don't throw them out, but this is the assumption done in the paper. And so you have this directionality of adoption. Here's another example. This is the patent race. So if two firms are making investments into the research and development, right, and they are trying to reach the goal, whoever reaches the goal first gets the patent, and that's an absorbent state of this process. So there are directional games out there where the methods, the approach that we will be talking about, that I will be describing, seems to be very relevant and helpful in the solution. Yeah.
So the absorbent state, trying to understand the role of it. Is it a computational role or what?
It will be a computational role.
Primarily computational, right?
It doesn't have to be a state, it can be a collection of states.
Collection state, yeah. Actually, but otherwise, like the directionality is got nothing to do with the absorbent state per se.
Well, if you have a finite stochastic game with directionality, you will have an absorbent set.
That's right.
Yeah. Okay, so let's go back to the strategy-specific partial order on S on the set of states. I'm sorry.
I guess you use the assumption that cost there's a cost equals 0. What if I could keep going down?
Yeah, not all games are directional.
You can have a direction game
which doesn't have the, well, if I say it's a finite state stochastic game, I think that implies.
Because the quality ladder game.
Yes, you have to normalize it, right? In order to make it finite.
There's an outside alternative that you're fighting against. That's
Which,
okay. Not saying your way to that.
Well, maybe we can think of how to extend the notion, right, and expand this. That's one of the reasons why we want to talk about that. That there are further applications and maybe other tricks that you can use and where you can use the idea from here. But yeah. So if I think about the strategy-specific partial order, I want to have an order in this directionality which is not dependent on the strategies, right? Now I want to somehow define the way to solve any game with any strategies in any strategy-specific partial orders, and the way to do this is to look at what's called Course's common refinement of these orders. So imagine that we put onto the picture all possible transitions from all possible, all admissible strategies. And that's what we have. And then, if it is a directional dynamic game, again, I'm skipping over a lot of details that you can find in the paper. Then this is a DAG, right? Directional cyclical graph. Well, except that we allow for self loops. And you can apply standard algorithms to work with this cyclical graphs. And in particular, what's possible is it's possible to partition the points in the state space into what we call stages. And you can see that each stage has a property that the points inside of the stage do not correspond. There are no areas in between them. And all of the stages are totally ordered. Okay, that's where we take this directionality given by partial orders on the points in the state space. And you can think of an algorithm to get this, right? You first find all the points which don't have errors coming out of them, delete that, or put them into one stage, delete that, look at the rest of the graph, repeat this process. And if it's finite, then also it means that you don't have any loops. So it's fairly simple. All right, now let's think about the subgames. If we have, we can think of a game that starts in any given point in the state space. And from just the structure of the transitions, we show in the paper that in order to solve the subgame of this whole game that is given by all of these points here, you can actually restrict yourself to the continuation strategies, which are optimal actions in that one point, taken together with the optimal actions, optimal strategies on the dependent stages. Okay, does it make sense? So in order, where it takes you is that in order to now solve for the Markov perfect equilibrium of this remainder of the game, of the stage game, you only have to look at the continuation strategies at one point. And that's the key. Now we're breaking the huge problem of computing the Markov perfect equilibrium for this whole structure into just looking at one point in the state space. And here's how it goes. This is what we call stage recursion algorithm. Right, first look at the stage with the absorbing points. The game is really simple there because there's no further transitions in the industry. It just stays there forever. It's still fine at infinite horizons, but we can solve it fairly easily. It's the equilibria defined by a small system of equations there. And once the solutions here are found, this solution, then we can solve this point by taking the already found solutions and attaching them to the optimal actions in this point. And you can also see here that we can solve each of these points in parallel. They don't communicate. So the optimality is described there by equations which only depend on the things which is already solved for. And we can just take another step and now use the combination of the last two stages and sort of go in the backwards induction as if you were solving a life cycle model, right? And then you solve the whole game. So this is very simple. I'm sorry, very close to a normal backwards induction. So the analogy is very direct. Instead of time, which evolves from t to t plus 1 deterministically, and you use this direction of time to solve a dynamic problem. Now we are talking about the partial orders and transitions are stochastic, right? But we can define this one direction in this game and use that direction to go backwards and solve the game by following the state transitions instead of time transitions. Okay. Any questions at this point? Now let's talk about multiplicity. So if we encounter multiplicity at any point of this process, how would it manifest itself? Well, there would be multiple equilibria in one of the points in the state space. And so if that happens, then we need some sort of equilibrium selection rule to be able to carry on this state recursion. So here's an example. I'm looking at a smaller game here, but imagine that I've solved it in the absorbing state. There's a single equilibrium here. I solved it on the edges of the bottom plane of the pyramid. There are single equilibria there, but then I went into the interior point and suddenly there are three equilibria. Now these three equilibria, we can think of them as kind of the static model that Bertel was talking about. And here's the illustration from one of the solutions of the leapfrogging game. Here, the equilibrium correspondences are this, lines with 90-degree angles. This is because we have eta equal to 0, right? So if we don't have any shocks in these decisions, then we're talking about mixed strategies and the intersection points of the best responses, which are deterministic. And we can have 5 equilibria. We can have this lower level, lower right panel with 5 equilibria in a stage game. Now, if eta is greater than 0, everything starts being smoothed out, and the best responses look, a little bit more interesting. And you would expect that there is some sort of convergence from along the eta, and this is really true. So if you change eta, then in solving each of the stage games, you can see this convergence of best responses to the deterministic solution. So deterministic choice rules.
Yeah, so the equilibrium selection rule is primarily for computation again, or
so here I'm thinking of this as computational.
Because if you had multiple, you could have done it one for each possible selection, right?
Exactly. So what I'm saying is that if I ever encounter a multiplicity, I want to have some sort of a rule that tells me, okay, use equilibrium number 1 over there to carry on backwards induction. And in this sense, equilibrium selection rules, they just become vectors of indices, right? I can write a vector of, with one digit corresponding to one point in the state space, and I can fill it with indices and say there's k equals 3, the maximum number of stage equilibria that we could probably show. Now I just showed you the case of 5, but the point is that I can write all of the equilibrium selection strings, now we can call them, right, in the lexicographical order, for example. And the task is now to search for those strings which make sense. In which sense? Which index the equilibria that actually do, that you would encounter in the solving of the stages. But the point here is that it's very simple. It's very easy to write all of them, which means that we will find all of them if we just go one by one through this list. But we can do better. So to do better, let's think about the dependence of the solutions in this game. We have directionality, and that means that the solution, higher up here depends on lots of solutions in different points on other points of the state space. And the solution in the absorbing state, it's basically independent, doesn't depend on any other points in the state space. We can use this dependent structure to order the digits in our equilibrium selection string so that, the lowest digit, that's the one which is most dependent. So that would correspond to the top of the pyramid. And the highest digit is the one which is most independent. And that allows us to kind of jump over the blocks of this huge list. Because if we just remember how many equilibria we've encountered when we've used the first equilibrium calculated in each of the points, right? Then if there's only one in a particular point, then you don't have to spend time to try to search to check, right? This other two strings which would point to a second or third equilibrium in that particular point. And so in that sense, the search problem of this equilibria is greatly simplified because now you know how to jump over huge blocks of this big table, including all possible equilibrium selection strings. Yeah. Well, that leads you to this RLS algorithm, recursive lexicographical search. Oh, I didn't talk about recursiveness. The recursive idea comes from the fact that, if only a couple of digits on the right changed, you don't have to recompute the whole equilibrium of the whole game. You just need to recompute that little tail that could have changed. And in that sense, you're recursively recovering Markov perfect equilibria. So that's the name of the algorithm. What's the algorithm? Well, you start with the equilibrium selection string of zeros. You apply stage recursion algorithm to that. Then you remember how many stage equilibria you found along the way, and this is called this NE of ECR. And then we define in the paper the successor function, which adds 1 to the equilibrium selection string using the variable base arithmetics, where the bases are given by this number of equilibrium stages. It's all very complicated, but people doing close to computer science here in the room will recognize immediately that what we're doing is really just a tree traversal. Tree traversal deep first. And to understand this, I'm using the same indices that were used in indexing the points in the state space, with the 14 being least dependent. And least dependent, you remember, that's the one which is absorbing. And really what we're doing is we're calculating the equilibrium by going through all of the stages and then remembering where there's branching, where there are multiplicity along the way as we calculate this equilibrium. And then all you have to do is to come back to the last branching. Like here, for example, it comes back to this point over here and continue extend the branches as we go, right? And so this is essentially, this is the RLS algorithm, which, after a few years working on it, turned out to be a very, very simple tree traversal. So it's, a lesson here is that it's very good to think about your problem in unusual settings and transform it to something that might be already solved. Anyway, so the main result in the paper in Riefstad is this theorem, which says that if there is a way to solve every stage of this dynamic game, of directional dynamic game, and find all equilibria, then RLS algorithm delivers all Markov perfect equilibria of the whole game. And the way, the proof is constructive, I just showed you. But you can also have a weak version of this theorem where, if you can recover some and at least one equilibrium in every stage, then you can potentially check for multiplicity of a directional model by just exploring whether there are multiple solutions in some of the stages, and then still combine those multiple solutions in the way that RLS shows to construct a set, right, of equilibria in the game. Now, it's very important to notice that solving even a stage game might be a very hard problem. So essentially what we're doing, we're generalizing the notion of backwards induction in this approach, generalizing it to the transitions on the state space. And then we're breaking up the huge problem of solving all of the Bellman equations and all of the best mutual best responses for the whole problem into a set of small problems. Is that clear? And of course, each small problem can still be extremely hard. There's no surefire way, let's put it this way, to solve a nonlinear system of equations, which you would have to do for each small stage in this dynamic game. But there are nice properties too. So, for example, here we're trying to illustrate that for different discretizations, you can have a huge upper bound on the number of equilibria. And this is a number of rows in this big table, right? And so in this example, for example, simultaneous move game, we spend 45 minutes on a laptop to find almost 200,000, 200 million equilibria out of this number, which I don't know how to pronounce.
Well, it's 174 septillion, all right?
Yes.
It's a lot.
But if you happen to have just one equilibrium, which sometimes happens, then you don't spend any time on the search part of this algorithm. And that's because, the tree only has one branch from the roots to the very end. Just follow that and you verify that there are no other equilibria. That's it. All right, so let me spend just a few minutes on the resolution of the Bertrand investment paradox and the theoretical results of the leapfrogging model. I should stop here probably and ask for questions for a second. No, nothing online.
No questions.
So you have to keep all potential equilibria in memory, or
Well, you have to remember where it branches.
remember where it branches. I see. And so, like, the number of potential branches is what the complexity is.
Right, that's right.
In addition to the heat stage.
Right, but see here, it was branching here, and this is a real example, right? But if we selected this equilibrium on this stage, then there's no branching down below. So it's really, you have a theoretical upper bound on the number of equilibria in the stage, and that creates that huge number. But how relevant is that huge number? It's unclear, probably not so much.
So if we change this, we have a finite number of states that move you backwards one.
Which
A number of states I could move back to somebody else beats,
it's a regenerative process.
one of these states. I could still do your thing.
Wonderful.
And so it is actually somewhat more general. I mean, I could do the directional thing on each state, then I have to put it together. You shouldn't get me wrong, but I guess it depends how I switch.
Yeah, I think if I understand you correctly, you're absolutely right. So in the paper in Riefstad, we're actually talking about splitting the state space into directional dimensions and non-directional dimensions. And then on each point, on each of those dots, you could have a stack of states that you have to solve together.
So
If they're multi-directional, yeah, absolutely.
if there was a transition agent between these other states that
It would be just block.
you would get back to the kind of thing we were doing. And I'm wondering just what the computational comparison.
Right. So I guess the point here is that you can find some directionality, right, in more general setups.
I think at least in the games that we do in IO,
Right.
I mean, there is a directionality conditional on this other aggregate state that's moving the whole industry. Nobody does worse. You know, people try and do better,
All right.
but the only reason it's worse is because the world is working against you.
Right.
So
So on top of the general direction, there's a little bit of stepping back. That's what you're saying,
yeah,
in some sense. Okay.
I don't know. I think
This is very interesting. So I guess the reply would, if this coming back, even for a short distance in some metric, is overlapping, then probably this cannot be applied. But maybe there is a generalization where you can apply this algorithm and then have some sort of iteration. You know, you could think of what's the minimum number of links that you have to delete to get directionality, for example, and then yeah, work with that. Yeah. Thank you. All right, so this is another point to make about the next few slides, is that you know, we've set out to solve the model and to see whether leapfrogging is even possible and what are the typical equilibria in this setting. But then we've worked so much with this model computationally and numerically that we started kind of proving some of theoretical results. And so the next few slides are theoretical results in a different paper. But you can show that the no investment, if the investment cost is not too high, is never a part of any equilibrium, any MP equilibrium, either in the simultaneous move or the alternating move versions of this game. And in fact, you have all sorts of different properties, equilibria with different properties. So leapfrogging turns out to be very typical. You have preemption MPEs, where all of the investments are done by one firm. And you know, the other firm never has an incentive to even try to invest. And that's kind of a sad outcome. You have duplicative investments. And so you have, well, should I just turn to the picture? Just a second. And the inefficiencies in this industry primarily come from overinvestment, so somebody investing too often compared to the social optimum, or investing in the same time, so duplicative investments. Interestingly, we can prove the sufficient conditions for uniqueness in this game, and they happen to be, we don't have, so the sufficient conditions turn out to be that the firms have to move in alternating fashion. And interestingly, it doesn't matter whether it's deterministic alternation or stochastic alternation. And then the second condition is that the technological progress has to be strictly monotone. So at each time, you know, at each time period, the probability of the state-of-the-art technology to remain the same has to be 0. And that seems to be a bit strong, I guess, in application. So we don't have necessary conditions, unfortunately. But generally, equilibrium generally is not unique. Okay. Now, you know, we can, once we've computed all of the equilibria, we can start making plots like this. And these are the payoffs from different equilibria to the two firms. And the diagonal gives you the expected discounted value for the monopolist. So expected profits from the monopolist. The feature which is really amazing here is that the fully monopoly outcome is an MPE. So you have an MPE where only one firm does all of the investments, and they also do them at the optimal times to get to the monopoly payoffs. And probably it has to do with the way that we are modeling demand in a very simple way. But you also have support for the Bertrand outcome in this dynamic game. Now, these are the payoffs for the simultaneous move. If we looked at some sort of alternation, then the set of the payoffs and the set of equilibria shrink and become the interior. We can show that this is interior of the triangle. And also, you know, picture changes quite a lot depending on which assumptions you're making on the transition probabilities of the improvements, right? So this is simultaneous move with deterministic technology improvements. All right. Let me skip all of this. Or maybe I can stop here. So we never impose symmetry assumption. But if we did, and we can just pick out the equilibria which satisfy the standard symmetry assumption, they happen to be on the diagonal over here quite in the inefficient range, right? The efficiencies, the equilibria which are closer to the frontier. So at least in this model, imposing symmetry actually, knocks out a lot of interesting equilibria. This is simultaneous move version. And I guess another thing that I want to note before we're coming back to estimation is that the full solution homotopy is a really promising method as well to solve this sorts of to attack the problems with multiple equilibria. And in our model, we can actually have a wonderful parameter to do this homotopy along, and that's the eta, the scale of the extreme value shock. If eta is large, like in this graphs around what 1.5 or 1.4, then all the competitors basically are flipping the coin, right? Everybody's doing random choice, and there's a single equilibrium. But then you can draw this equilibrium, this correspondence. You can, as you decrease theta, then the equilibria can be reconstructed. But because of this complexity of the problem in the number of equilibria, the number of bifurcation points along this homotopy path is just astonishingly large. So in this setting, at least with simultaneous moves, where we have this very large number of equilibria, it seems that the homotopy will also have trouble following, the path through all of them. All right, are there any questions about the solution of this model? All right, so let me come back to estimation. And I guess the main point here is that now that we have this model, which is very hard and which we can control fully because we can fully solve it for all Markov perfect equilibria, can generate data from any of them, we can come back and test different estimation approaches, different estimators. And so let me just come back to this, define a set of Markov perfect equilibria that we can recover from the full solution. This set is basically a collection of choice probabilities and value functions that satisfy, you can think of psi v as the set of Bellman equations, a really large collection of Bellman equations, and the choice probability formulas here, the best responses. And let me also introduce the gamma, the Hutt-Millian version. And then, coming back maybe to the same thing that Bertel has already said, we can have different approaches based on CCP, including the minimum distance and pseudo likelihood. NPL, we should actually mention this this recent paper by Gaberia and how do you pronounce it? Marquardt? Which goes deeper into the properties of the NPL estimator. And having this paper out really slowed us down because now we want to use equilibria very accurately, which select data generating equilibria very accurately, because as you will see, we're not really doing justice to NPL in our Monte Carlos. Okay, and then we have MPEC, and I'm mentioning the homotopy approach to maximum likelihood estimation here as well. So the idea that we have is to construct a nested estimator from the full solution approach. So this can be called nested RLS, right? With the idea being that if you have data from M-independent markets and time periods on actions and states, you can maximize over the space of parameters, the likelihood function, but then this is the key. The likelihood function has to be maximized over the set of equilibria. And that's the approach. So if we can solve for all equilibria, then we can calculate the likelihood of each of those equilibria and maximize over a discrete set of equilibria, which of course makes the problem very, very hard. And takes it back to what Bertel was showing for the static game. Yes.
So presumably you want T to be big relative to the number of markets, right? If it was a cross section, it would be like with so many equilibrium, it would be like an incidental parameters problem, right? Finding the equilibria one per market. So you want to observe each market for a long, long time, presumably.
Yeah, I think we're still discussing, how to do asymptotics here. But yeah, thanks. But what's from the computational point of view, what's interesting here is that we have this wonderful structure of the RLS tree, the tree that we've been traversing while solving the model. And we are facing a discrete programming problem here. We have to maximize with respect to a discrete variable, a likelihood function, which is defined in a standard way, right, with the sum over markets, players, and actions, I guess, and times. An old approach is branching bound algorithms for solving integer dynamic problems. And it seems that we have all of the needed components here. And I don't have much time left, but let me just talk about this one picture. So this is the implementation of the branching bound algorithm for solving this internal, the maximization problem over the discrete finite set of equilibria. So what we have here is that, again, the state space is indexed. We have every point in the state space organized along the x line. We again preserve the dependency that we've talked about already. The histogram, these bars, this represent data. Okay, data is distributed in the state space somehow, we can calculate what we call partial likelihood. So imagine that we only look at the data that corresponds to the absorbing state here, 0, 0, 0. This one, the one on the left. It will produce some value for the likelihood. And as we solve the model and traverse our RLS tree, we can update the value for this partial likelihood by only calculating likelihood on the portion which is already computed, on the portion of equilibrium where we already know the choice probabilities and the value functions. And that means that we can now rank different equilibria in terms of their likelihood contributions. And the likelihood does decline, right, as you add more and more data. So this is very convenient because we're looking for the maximum of this decline functions. And these are what all these black lines represent. These are likelihood computed for particular equilibria corresponding to the branch on the RLS tree. And the idea of branching bound is that once you reach some sort of one of the records, once you go through this whole process all the way, then you will know the level of the likelihood, which defines kind of a cutoff where you don't have to compute the likelihoods that are not looking promising anymore. Okay, does it make sense? So if I go through the RLS tree once and compute one equilibrium, we can compute a level of the likelihood for all of the data. And imagine it becomes here. That means that in none of the other equilibria, we need to continue once the partial likelihood reaches that level, because the partial likelihood can only decline. And we're looking for the maximum. That's the idea here. And then, as you go through this, you find the exact solution over a finite set of equilibria to the problem of maximizing likelihood over this set. And the reason that we can do this is that we have this nice tree structure of the equilibria that we've discovered and that we've described right to the in the solution, and the fact that by adding more data to partial likelihood, this function can only decline. Now it's the computational question is, what data would be good to distinguish between different equilibria? And so if these levels here are, where are they? How much of the equilibrium tree can they cut off before, so to allow to save time on this calculation of solution with the estimation in the same time. But another approach is that we don't really need to use the exact deterministic cutoff rule here as well. So maybe we can, look towards econometric techniques and have some sort of a rule that would allow to approximate the equilibrium with the maximum likelihood, rather than find it exactly as the branching bounds would do. So we're thinking about some sort of Pauli algorithm here. Oh, I don't have time to go through the Monte Carlos, but let me take 1-2 minutes more maybe. So the Monte Carlo setup is similar to what Bertel had shown for the static games. We want to look at the simple problem where there's theoretically only one equilibrium in the model and things work really well in that case. We want to look at the second case scenario where there are multiple theoretical equilibria, but the data is only generated by one of them. And then finally, we want to look at the case where different markets play different equilibria. And we want to identify which equilibrium is played in which market, which seems to be possible, at least theoretically, since we compute all of them. Okay, sorry, I ran out of time. What's important to say here? I guess the takeaway message is that in the simple case, all of the estimators work, and the CCP, this two-step estimator, is of course the fastest. The maximum likelihood estimators produce exactly the same results. As you increase multiplicity from 3 to say 81 potential equilibria at the true value of the parameter, then NPL just completely falls out of the picture. So NPL fails to converge, probably because we're using unstable equilibrium. We're still investigating that. And as Bertel was showing, the MPAC approach, and we have two here because you can reformulate the MPAC in terms of the value functions and choice probabilities in this dynamic sense constraints, or you can convert all of the constraints and say, for example, choice probabilities, as we do here in the fourth column. Well, you see the same behavior. So MPAC starts converging to the other equilibria than that generated the data, and you can see that by both the differences in the achieved likelihood and in bias and standard errors. Now, what's interesting to point out is that these two lines here, they are here to show whether we have achieved the equilibrium, where we converge to the equilibrium in the sense, that the choice probabilities, the mutual best responses conditions are satisfied, and the value and the Bellman equations are satisfied. And you can see that, two-step estimators, they do not impose these conditions, and therefore you have discrepancy if you want to try to check whether at the estimated parameter you are actually at the equilibrium. Whereas MPAC always achieves an equilibrium, but it seems to be a wrong equilibrium, not the one that generated the data.
Last question.
Yeah.
The MPL, you say it's not convergent. Does that mean it's just cycling? What's happening?
Yes, that's a very good question. So in this Monte Carlos, we limited to 30 iterations just to see whether it converges to, directly or it doesn't. So maybe it's also not a very good test of NPL here. Okay, let me stop here and leave you with, the conclusion that if you really study the structure of the problem, and if the problem happens to be directional, then maybe not all is lost for these full solutions, and maybe an approximate solution based on the full solution approach may be useful, especially in the multiplicity case. Are there, yeah.